We will continue the topic with probability.
To extract meaning from chaotic variables, we rely on probability. This is the foundational mathematics of inferential statistics, the specific discipline of using sample data to make predictions and test hypotheses about a larger population. Within this framework, every chance process is treated as an experiment that leads to well-defined results called outcomes. To calculate risk, we must first map the sample space. This is the absolute set of all possible outcomes for any given probability experiment. Before calculating a single fraction, we establish the boundaries of this space. Every possible result must exist within this enclosed boundary. The lower boundary is absolute. If an event is mathematically impossible, containing no members in the sample space, its probability is exactly 0. Conversely, if an event is absolutely certain to occur, its probability is exactly 1. Therefore, all valid probability values, whether expressed as fractions or decimals, strictly range between and include 0 and 1. This leads to the most critical axiom of the entire system. The sum of the probabilities of all distinct outcomes within a sample space must perfectly equal 1. Defining this bounded mathematical space is the mandatory first step before any predictive modeling can begin. It forces us to abandon intuition and rely entirely on geometry. Within these boundaries, uncertainty is quantified using an epistemological triad. We rely on 3 distinct analytical frameworks, depending entirely on the specific nature of the data environment. The first framework is classical probability, which applies exclusively to closed theoretical systems. In classical probability, we assume that all outcomes in the sample space are equally likely to occur. Because the mechanics are perfectly known, absolutely no real-world experiment is needed to derive the math. Consider a quality control scenario. A sealed batch contains exactly 100 cans. Internal inspection proves exactly 5 cans are defective. Randomly selecting one relies purely on deductive logic. The probability of choosing a defective unit is 5 divided by 100, or 0.05. We pivot to the second framework, empirical probability, when theoretical odds are completely unknown and cannot be deduced through logic. Empirical models are built entirely on inductive logic. They require a physical sample size and actual recorded frequencies from past events to estimate the likelihood of a future outcome. This line graph tracks real-world cold chain hygiene. A company observes 1,000 milk cartons over a 30-day month. Observation data reveals 40 cartons spoiled before their expiration date. The empirical probability of spoilage is 40 out of 1,000, or 0.04. The choice between classical and empirical frameworks hinges entirely on whether you are analyzing a mathematically closed loop or observing physical degradation over time. There are environments where true uncertainty lives, situations possessing no theoretical bounds and absolutely 0 historical data to observe. This requires the third framework, subjective probability. Imagine a product development team preparing to launch a completely novel, plant-based snack. There are no past sales figures to run an empirical model. The team must synthesize highly variable, unquantifiable factors, such as shifting market trends and initial sensory panel feedback. They combine these variables with their own professional experience to make an educated estimate of the risk. This process yields a heuristic, subjective probability. The team might assign a 70% chance of product success, completely absent of formal mathematical proof. While subjective probability lacks the rigid calculations of the other frameworks, it remains the only viable method for strategically forecasting completely new innovations before empirical data can be gathered. Once a framework is chosen, analysts must map the internal boundaries of the specific outcome they are tracking to manage the data effectively. We define event E as the specific target outcome within the bounded sample space. We then identify complementary events, denoted as E'. This is the set of outcomes not included in event E. E' is simply every outcome falling outside your target. Recall the absolute axiom from our first step. The probability of all outcomes in the entire sample space must sum perfectly to 1. This gives us the complementary rule equation. The probability of E' is exactly 1 minus the probability of event E. In complex risk assessment, this rule is highly practical. Instead of calculating hundreds of complex individual outcomes, analysts isolate the probability of the specific outcome they do not want and subtract it from one. Utilizing complementary events is an elegant mathematical shortcut that drastically reduces the computational workload required to map a system. Real-world problems rarely involve single, isolated events. Variables cluster together. Analyzing these compound events, situations with two or more outcomes, requires the application of the addition rules. We must first check the data for mutually exclusive events. Mutually exclusive events are disjoint outcomes that share no common traits. Because they share nothing, they physically cannot occur at the exact same time. A patient cannot simultaneously possess purely type A and purely type O blood. The rule here is straightforward. To find the probability of selecting a person with type A or type O blood, you simply add their two individual probabilities together. The structural danger lies in non-mutually exclusive events, where variables are permitted to overlap. This matrix table maps a pediatric staff. We must calculate the probability of randomly selecting an employee who is either a nurse or a male. The data shows 8 total nurses and 5 total males out of 13 staff. Blindly adding them, 8 plus 5 equals 13. Mathematically, 13 out of 13 yields a probability of 1. This incorrectly implies a 100% certainty that anyone you pick will be a nurse or a male, erasing the female physicians from reality. Look at the mechanical error at the intersection of the matrix. The datasets overlap. The male nurses were counted twice. To restore mathematical reality, we apply the second addition rule. Add the two totals, then subtract the probability of their intersection from the calculation. Failing to map these structural overlaps causes the integrity of an entire probabilistic risk model to instantly collapse. Probability serves as a rigid engineering tool for managing the void of uncertainty. Analysts must accurately diagnose their data environment, choosing to apply classical, empirical, or subjective frameworks based on the evidence available. They must rigorously define the absolute boundaries of the sample space to calculate limits and exploit complementary shortcuts. And they must aggressively audit their compound events, ensuring non-mutually exclusive overlaps do not corrupt their equations. Mastering these bedrock axioms provides the mathematical stability required for advanced inferential statistics, from basic sampling plans to modern.
Thank you. Disclaimer: Artificial intelligence, AI, was used in the development of selected instructional materials in this lesson. The use of AI is intended to enhance clarity, visualization, and learning engagement. While all academic content has been reviewed and guided by the instructor,